In this problem, we're talking about Drew, who is the landlord of an apartment building, and he's looking to remodel one of the floors in his building. There's two types of apartments that he can build, small ones and large ones. And then it says there are currently 10 sections of the floor. A small apartment fills one section and a large apartment fills two sections. According to the building code, he can have at most 7 apartments of any size on the floor. He charges $800 for small apartments and $1,100 for large. How many of each size and apartment should he build to maximize his profit? So first step is to define our variables. The two variables are the two things that we're talking about trying to maximize, which is the two different size apartments. So I'm going to say that X is going to equal the number of small apartments. And then Y is going to equal the number of large apartments. Okay, for our constraints, there are two constraints that are not in this problem, but they're something that we need to have as part of our constraints. And those are that X and Y both have to be greater than or equal to 0, because you cannot have a negative number of apartments. You could have 0 apartments, but you can't have a negative number. So those are the two that aren't in the problem. But now let's talk about the ones that are in the problem. So the first thing I want to take a look at is where it says currently there are 10 sections of the floor. A small apartment fills one section and a large apartment fills two sections. So 10 is like our total. That's how many sections of the floor he has to work with. So that's going to go on the right side of our inequality. And then we're going to multiply the number of sections that each apartment takes up times its variable. So one section is how much a small apartment takes up. So I'm going to say 1x. And then if we add 2y, that's 2 sections for each large apartment. There are 10 sections total. So he could take up as much as 10 sections or less. So this is going to be less than or equal to. The next sentence, it says, according to building code, he can have at most 7 apartments of any size on the floor. So that means if I add up the number of small apartments and the number of large apartments, there can be at most 7 of them. At most is a little bit misleading. It makes it sound like it should be greater than, but at most means you can have, like 7 is the most you can have, or you can have less than that. All right, for step 2, we need to graph our constraints. Now the purple ones, those are almost unnecessary. All that the purple constraints do is that they limit us to the first quadrant. And if you look at this blank graph that you're given in step 2, it is already limited to the first quadrant. So if I graphed the inequality x is greater than or equal to 0, it would be this line right here, and then I would shade everything in to the right of it. If I graphed the y is greater than or equal to 0, it would be this here, and I would shade everything above. So basically those two inequalities limit us to quadrant 1. So even though they're necessary to write as part of our constraints, they aren't exactly necessary for us to graph. So I'm going to erase them because otherwise our graph's going to get looking kind of messy. All right, so let's take a look at the orange inequality. That is not in slope-intercept form, so I'm going to rewrite it. And you'll notice that I didn't rewrite the 1. The 1 is unnecessary. I wrote it there just so you could see where it came from though. So I have to subtract my x term. So I would have 2y is less than or equal to negative x plus 10. And then if I divide everything by 2, I end up with y less than or equal to. This is really like negative 1/2 x plus 5. There's like really an invisible negative 1 there. You can't see it. I like to write it as a fraction, and that way you can see the rise and run. So I'm going to go to my graph. I'm going to put my y-intercept at 5, and then I'm going to go down 1 and right 2 until I hit the x-axis. This is going to be a solid line because it's less than or equal to. And since it's less than, what I'm going to do is I'm going to shade everything that's underneath this purple, underneath this orange line in yellow. So that would all be less than the orange line. Now let's take a look at the green line. I'm again going to have to rearrange. So I have x plus y is less than or equal to 7. I'm going to subtract the x term. So I would have y is less than or equal to negative x plus 7. So my y-intercept is 7 up here. And then when I do my slope, it's going to be down 1 and right 1. And it's really important for me to make sure I see exactly where they cross. So you see how this point just went right over another point? That's going to be really important because that's going to be one of our critical points. So I'm going to connect the dots of the green line, and I'm going to shade below this graph also. So everything that is underneath the green line is going to get shaded with blue. And you'll notice that some of the shading is turning green. And the part that's turning green is the part where the two sections overlap. And that is what our feasible region is. So this section right here, I'm going to try to make it more obvious. This section right here that I'm shading in, that's called our feasible region. And the points that we really care about for step 3 are the critical points. And those points are the corners of your feasible region. So this one, this one, this one, and this one. So there's 4 of them total. So I'm going to write those down. The first one is 0, 0. And then if I go up, that's the point 0, 5. This one that's kind of in the middle is the point 4, 3. And then the last one on the x-axis is 7, 0. All right, so now the next thing is to test each critical point in the objective function, which I just realized I skipped. So I'm going to go back and do that. The objective function of this problem, we're talking about the objective, like what are we trying to do? And what we're trying to do, it tells you in the very, very last sentence, is maximize profit. So I'm going to make my objective function p of xy. I like to use P for profit, or if we were doing cost, I would use C. It says that Drew charges $800 for small apartments and $1,100 for large apartments. So that's money that he's charging for rent. That's coming into him as profit. So our objective function would be 800 times the number of small apartments, or X, plus 1,100 times the number of large apartments, which is Y. So that's the function that I'm going to be plugging these critical points into. So I'm going to do this one at a time. So I'll do P of 0, 0. Now if he rents out 0 apartments of each size, he's going to make $0. So even though 0, 0 is one of our critical points, it's kind of unnecessary. You're not going to make any money if you don't rent out any apartments. All right, our next critical point is 0, 5. So that would be if he rented out 0 small apartments and 5 large apartments. And that would be a profit of $5,500. Our next critical point is 4, 3. So that would mean he would rent out 4 small apartments and 3 large apartments. If he did that, his profit would be $6,500. And then last but not least, if he did 7 small apartments and 0 large apartments, that would be $5,600. So I'm looking for which one is giving him the biggest profit. And the answer to that is this one right here. So $6,500 is the largest amount of profit he would make. So the final answer to this problem would be that he should rent out 4 small apartments and 3 large apartments.